So we're really delighted to have Professor Sue Carter with us here this afternoon. She comes to us from the Santa Cruz campus. She earned her Ph.D. from the University of Chicago and worked at AT&T Bell Laboratories as a postdoc and at the IBM Almaden Research Center as a visiting researcher before joining the faculty at UC Santa Cruz in 1995. She is a professor and associate dean of graduate studies. Her research focuses on thin film optoelectronic devices and technologies for sustainability. So she'll talk with us a little bit about that today. She's currently the UC Santa Cruz Faculty Climate Action Champion and Director for the Center for Innovation and Entrepreneurial Development, which she'll also mention, I think. She's been very involved with the entrepreneurship programs on the UC campuses, as well as prior to that and outside of the UC context, and has launched 3 startup companies ranging from photovoltaic technologies to K-12 science education. Please join me in welcoming Professor Sue Carter.
Thank you. So I'll be frank with you right now. I want to start by thanking you for inviting me. This is great. This is the first time I've been up to Citrus at Berkeley, and it's been probably a decade or so. Well, actually, I'm part of the BAPV consortium, which is up here, but it's been quite a long time since I've been at Berkeley, so it's great to be back. I'm going to put a caveat here and tell you I'm not going to talk very much about my research at all in this talk, and this is also the first time I've given it, so it might be a little bit rough, but I will talk a little bit about some of the stuff coming out of more of our entrepreneurial efforts, and, oh, that's interesting. Okay, whoops. So this is just a slide just to give you an idea of, we talked about startups. These are some of the things, we're talking about climate change and entrepreneurship, so I want to give you some of the ideas what I've done in climate, an entrepreneur that's related to climate change, and I'll explain this later. My very first company I helped start back in 1991 called Advision was really focused at that point on something called fully printed organic lighting displays. We basically the innovation was that we were able to take OLEDs and instead of use vacuum-based processing, we were able to use the same technology used to print T-shirts to print organic lighting displays. This company was end up being partnered with Cambridge Display Technology, which has the OLED thing. It's responsible for the OLEDs coming out right now in phones and other things, and it was sold actually in 2011. But basically, this was kind of one of the early introductions was towards trying to make things a lot more energy efficient to reduce our carbon emissions. We then went to this company called Selexent. Selexent failed. It was a fully printed CAD-TEL company. Well, it didn't completely fail. It actually came back and got reinvigorated as a company called Siva Power, which now does manufacturing equipment for SIGs. But this was kind of one of my forays into renewable energy to reduce carbon emissions. I've since been working at the nexus between food, water, and energy in the company Soliculture, and I'll mention a little bit about that. But then most recently, I actually I noticed the real estate prices were really low in Santa Cruz about 3.5 years ago. And so my entrepreneurial thing was to buy a building because, it was cheap. But then I had to do something with the building. And I was originally going to make an incubator, and I named it IRIS for Institute for Renewable Integrated Systems. The idea was I was going to make it an incubator for renewable energy startups. But then I decided after a while that I was much better off instead of trying to help the next generation of students kind of get involved with understanding the science and the technology. So instead I started a science academy, which we've been running for 3.5 years. And it's been very challenging for me because I've had to teach kids as young as kindergarten, first grade. It's the hardest job I've ever had, is teaching young kids. So I now appreciate our teachers a lot more than I ever have. So I want to give a little bit of some concepts of climate change and how I see it, and then lead into why, and this will be the segue into entrepreneurship, the role entrepreneurship plays. So this is atmospheric CO2, right, and temperature as a function of millions of years ago. And I put this graph up because so people just understand that, cycling between 10 degrees and 25 degrees Celsius, or things going up and down by 5 or 10 degrees, isn't all that unusual in terms of the history of the Earth. Early on, we were at very high parts per million CO2. We're down here at this very small number, but the Earth has gone through much higher levels of CO2 in the past, right? And what particularly I want you to pay attention to is this section right here. It's the Carboniferous Period. This is where we're burning. This is basically where we got most of our energy that we use today. And you can see that at the very beginning of this period, we were at about, we were near 20 degrees Celsius and 1,500 parts per million. That started dropping quite rapidly, and you can see that there was a sudden dramatic change where the temperature dropped quite dramatically right in the middle of this period. There was a huge die-off then. And so let me show you a little bit more about that period. And I've got a little cute little movie here. It's very small. Basically, this is what it looked like, or people's visualization of what it looked like. When it started 359 million years ago, it was about 35% oxygen levels. It was very warm and very wet, and we had very high CO2 levels. And that caused these very giant insects to form. They were the size of large birds. And we also had very swampy, vast swampy areas. And for various reasons that people don't entirely understand, there was some sort of climate change event where the sea levels fell 100 meters, and we talk about 2 or 6 meters now, but there were 100-meter changes back in our history. And ice covered Gondwana. And so this was basically what the continents looked like back in that time period. And this Pangea ended up happening after this period. But if you draw a line through this, you'll see that this is the area where you would have expected when this collapse happened for most of the fossil fuels, the fuels to deposit. And in fact, if you look at where you find the fossil fuels of today, you'll see there's a line through Saudi Arabia right here. It's largely at this line back where the continents were 300 million years ago. This ended in a very cold period. It went from 20 degrees C to 12 degrees C, and it got down to 300 parts per million CO2. So there was a dramatic shift just in this one period. By the way, it was this large drop that basically caused the amphibians, which were dominant earlier on, not to be able to survive, and the reptiles to become more dominant, and that's, of course, what led to the dinosaur age. Or no, I'm sorry, not the dinosaur age, but the rise of the reptiles that happened down to the next, further along in the history. So we generated all these fossil fuels pretty much all during this Carboniferous period where there was a large change in our climate. And it was this dying off of this huge biomass that was generated by the very high CO2 levels and the high temperatures that allowed us to store up the energy. And this is a graph of how we're using. This is the million barrels per day consumption of oil versus function of time. And this is a prediction made back by Hubert back in 1956 of what our proven oil reserves would look like. And what he predicted back then was that we'd peak somewhere around 2010, our oil reserves. Much later predictions were made here, and you can see there's lots of different models. And some people are predicting, you can't see this down here, but this is about 2100 on the graphs, and some people are, 2010, some people are predicting that we won't peak until 2100 or 2200 in terms of our amount of oil we consume. But it really doesn't make a difference whether it's 100 years out or 200 years out, because if you look at how fast we're burning these fossil fuels as a function of years, we can look at the history of man, and what you'll figure out is we basically are going to consume all of it in a few hundred years, right? So we call this an era. We're living in what is called the fossil fuel era, and this, of course, is having consequences for burning it all. Burning something that took 100 million years to deposit in a few hundred years is causing us is making us accelerate what would be natural, the climate change process. So this is a picture of where we are in climate change, past and present. You can show a lot of graphs here. Here I'm just going to show the temperatures of the planet. These are films done by NASA and NOAA, and this starts back quite a ways ago. You can see we're back in the 1800s, and what you'll see is you have cold spots up here, and what you're going to find, of course, is that you're going to start getting the poles are going to start heating up, except for, okay, this is almost done, right? We're hitting 1970s. And now you can see the big heat up that's happened in the last few years. Okay, so this is what's causing everybody's concern. That's what's causing the melting of a lot of the glaciers up here. And this is where we are right now. This is where we are at 2015. It was the hottest year on record. But you can see that a lot of the areas down where Antarctica stayed relatively cool, and that has implications for why we're not seeing changes as fast there as we are in some other areas. So the question is, what is going to look like in the future? And we don't really know. I'm going to start these movies going, and then I'll pause them in a second. What we do know is that it makes a big difference on whether or not we stick at 550 parts per million of CO2 in the atmosphere versus 800 parts per million of CO2 in the atmosphere. So I've got, up here, I've got the temperature, how the temperature is changing is predicted as a function of year. So you can see this is 2052, 2018, versus precipitation. Okay. So I'm going to pause these somewhere in the cycle so you can take a look. I'm sorry, I'm having trouble seeing the screen down here. Okay, so I'm going to pause this at 2080 so you can see this. And pause this one at 2080. So you can get kind of an idea of the difference between whether or not we're doing this at, and then I also want you to look at the water, the precipitation. Whoops, stop. You know, I study physics. I know that your eyesight gets worse. Between year 40 and 50, your near point gets worse and worse. And I'm just facing it now. I turned 50 this year. And I need to get glasses, but I haven't actually managed to do it yet because I'm not willing to admit that my near point's as bad as it is. Okay. So you can see that the difference between the two scenarios here. Okay. Now, it doesn't look as bad as you might imagine, but if you look at here, you can see this is a scale between 0 and 15. You've got these areas now being as much as 10 degrees Fahrenheit higher versus if you have down here where you have more like 4 to 5 degrees higher. And this is enough to basically change the sea level rise from about a meter to something like closer to 5 to 6 meters. And this is the precipitation, and what we're mostly concerned about, if you can see that if you're basically where we are in California, you're not going to see a huge change in precipitation. You'll see some based on these models. Of course, it might change. But what will happen, of course, is you have a big distribution of all our fresh water resources up in the areas where no one lives and where you're not going to be able to recover the fresh water. So that's a problem. And in fact, if you go to 800, you basically get severe droughts in much of the southern portion of the United States and the continent. So this is what everybody's, of course, concerned about and what we're working on dealing with when we talk about how to use entrepreneurship to help climate change. This is just to kind of reemphasize the fact what's going to happen to our area, right? Berkeley's right here. The red is kind of what happens if we have 1 meter sea rise. We're not going to be able to do anything about that, probably. That's going to happen anyway, so we're talking about mitigation. But if we don't slow it down, we're going to basically get a much broader range in which where the sea rise is higher, and you're going to get more flooding. What's particular concern for a lot of people is what's happening with the San Francisco airport. That one's going to be underwater probably no matter what we do, so we're going to have to deal with how to deal with the flooding. And entrepreneurship plays a role not only in necessarily slowing down the rate of climate change, but also what do we do about impacts that we know are going to happen. There's nothing we can do about it at this point. So there was a report that came out of University of California in 2015 called Bending the Curve. And the idea, of course, of this was that what we really need to do is we can't stop these things from happening. A lot of it's going to happen, but we can try to stop it. Instead of going to 800 parts per million, we can try to go to 550 parts per million. And there's ways in which you can look at it, and they actually divide it up into CO2 emissions and black carbon and methane emissions, which they call, when you combine that with the fluorocarbons, they call that short-lived climate pollutants. And you can then look at what happens if you do business as usual. This is this line. You're going to get at least a 3-degree increase. If you just deal with CO2 or the short-lived climate pollutants, you have these two. But if you can actually do both, you can mitigate both of them, then you can actually keep the temperature raised. It's something that's going to still cause a lot of damage, but not nearly as much damage as if we didn't. So this is called bending the curve. And to do that, we need to remove carbon, not just CO2. So the key is not just to remove CO2, we've got to remove all these sources of carbon. So the challenge is, of course, removing carbon. You all know that ways to do that is renewable energy. I'm not going to belabor that. This is one graph of many, and the data here isn't perfectly accurate, but I think it basically makes a point. And that is, you can look at all the types of renewable energies out there, and I'm not counting nuclear in here because it's not renewable, although nuclear has a role to play also, and I don't want to ignore it. Most of our resources are solar. We have wind resources that are really substantial, but we're going to tap them out. We need about an extra 33 terawatts, so you're not going to be able to get them all from wind. Biomass, unless there's a breakthrough in terms of how much you can get biomass per unit acres, you're kind of maxing out on our usable land. Hydroelectric has almost been entirely tapped. So we can gain more there, but not a lot. And the numbers for tides and ocean currents are very low. Geothermal is very low. So you're looking at solar and wind as the two primary sources. So the question is, what role does entrepreneurs, if any, help us transition to a low-carbon economy? And that's what I want to spend a lot of the rest of my talk on. So I want to learn a little bit from history because I think there's a lot of lessons we can learn from history and what doesn't work. And this is one. This is the discovery of the photovoltaic cell that happened, right? That was motivated by some work on photoconduction and selenium very early on. Then Einstein, of course, figured out the reason why selenium works is something known as the photoelectric effect, which of course led to his Nobel Prize and a big breakthrough in physics as we know it. And then it was Bell Labs who actually produced the solar battery. That was a complete accident at the time. They were really working on, they were working on the photoelectric effect, but on a completely different technology. It was kind of an accident that came along with their discovery of the transistor, which were both, of course, big entrepreneurs.
Turning sunlight into electricity. Scientists of the Bell Laboratories at Murray Hill, New Jersey demonstrate a solar battery which converts light into power. A small amount, yes, but a big first for science. It's a simple device made of strips of silicon, principal ingredients of ordinary beach sand. Enough light from a lamp to power this toy Ferris wheel. Lights on, she works. Lights off, the motor stops. The solar battery may lead to the realization of one of man's most cherished dreams, the harnessing of the almost limitless energy of the sun for man's use. Here, the silicon battery powers a tiny radio transmitter, which uses transistors in place of tubes. His voice is carried only a short distance, but larger batteries may
So, at the time period, now this is back in 1954, people had no idea what to do with these silicon photovoltaic cells. What happened though was that at that point there was a space race going on with the Soviet Union, and one of the very first applications of this was, and what happened was they were putting these satellites in space, and they could only last for about a month on batteries, and they would crash. And so one of the first applications of this was actually putting these in space. They actually launched them from 1954. They had them in space running the Voyager in about 5 years. It was one of the most rapid transition of basic research discovery to actually implementation that has been seen, especially back in then. So it was 1954 to 1961 was roughly the time frame. 59 was when they started developing it to launch it into space. But yeah. But I think they got it up by about 1961 was roughly when. Yeah, I'm sorry. I meant to say no. I'm sorry. I misspoken. Yeah. Yeah. So, anyways, the point is, and it lasted. They expected it to last for something like a few years. It lasted for 10 years, right? So it's one of the most impressive applications of technology. They got to 10% power efficiency very quickly. But the point is, this was a huge discovery. Okay. But it never really made it. right? We never, at the time period, it didn't look like there was a huge penetration. There was the government, of course, most of you know about, well, probably a lot of you here know about the 2010 Sunshot Initiative. This was launched by Obama. He was trying to basically claim, well, if we're going to transition to renewable energy, we need something that's really big. He commissioned the DOE to basically push technology forward. The DOE came up with this great graph that showed that if we do everything right, by 2020, we might make it to 50 cents per watt for the PV panel. We'll also decrease the cost of balance of systems in the power electronics, and we'll get to this dollar per watt target. And this was their target for 2020 back in 2010. And this is what happened. Remember this 50-cent number I told you, right? In 2014, we had 36 cents. Okay, we had hit the target 6 years ahead of time. And the reason for that was partly because, and we'll get back to this, that China had decided to go ahead and start ramping up the production of polycrystalline and silicon and other silicon facilities. And it went through periods of high cost. They were able to drop it down to something that was much cheaper than anybody at the time period imagined would be possible. That allowed them to basically clearly dominate the market and drop this price down very, very quickly. And no one anticipated this. And so what happened was this. These are a number of companies that got bankrupt, a number of entrepreneurial started companies that all these entrepreneurs went out and said, we see this DOE Sunshot Initiative. We can develop technology that will change the world. And the DOE and the government's going to help us and fund our companies. And they did. And Solaria was probably one of the most famous companies that went under. But you can see a huge number went under also, including some Chinese companies that couldn't deal with how fast the price dropped. Okay. So the point is, this is an example of where entrepreneurship didn't work. Okay? Right? The success was made. The people that discovered the technology was made back in 1954. They got into a few applications, but they never profited any money off of it. Bell Labs never made any money off the PV cell and the invention of that. And a lot of the money that did get made in this was not based on the people that invented the technology. It was based on the people that figured out how to scale up and deal with the scaling. So there's another example here. I'm going to look at wind power for a second. There's another one that, obviously is making a huge difference to our carbon emissions. This was basically the first example of a wind power. Wind's been around for 1,000 years or so. They needed the DC generator, of course, and that came out in 1867. And very shortly after that, or relatively shortly, 20 years after, someone actually combined the windmill with the generator and actually made the first wind turbine that generated electricity. This was done by Brush back in 1888. This was his design. He had a 17-meter wind turbine. It took a decade for the modern wind industry to transition that. 1985, we started with basically the same size rotors that he had developed back in 1988. And then the wind basically just was kind of the wind industry is progressing quite a bit for the last 15 or 20 years, but all they're basically doing is making basically engineering changes on a design that's been around for 50 years or so. So this is what's happened. If you're curious, this is what's happened to wind power. A lot of the wind companies are now going bust. And that has a lot to do with the fact that there's some fears that the subsidies will take away, and if they don't have the subsidies, the business is not viable anymore, right? So this is a big issue. So wind is another example where entrepreneurship really hasn't lived up to the dream we thought it is. The entrepreneurs haven't been leading the transition to using renewable energy to save the world. It's really been more of the manufacturers and engineering that have figured out how to scale this up quick enough based on inventions that have been very old to make it. So I want to look at a couple bright spots, however, where we are starting to see entrepreneurship, people that are entrepreneurs really, I think, start making a difference. And this is LED lighting. 1962 is when the red LED light was invented. That was by GE. GE actually has tons of patents on this, and they were able to use those patents to basically generate a very viable, become a leader in LED lighting. So that's an example of the entrepreneurship really being beneficial here. And then Nakamura, of course, who's a faculty member at UC Santa Barbara, was able to miraculously develop blue light emission from gallium nitride LEDs, and he was able to do this with very little resources, with Bell Labs and everybody else throwing everything but the kitchen sink at it, and he did it in his lab with a simple innovation. So these are examples, I think, and this was a fairly rapid turnaround. This was 1993, and now we're about 20 years later, and LED lighting is now becoming ubiquitous in the house. So. And then there's one other thing I want to mention, because this is the other thing that's really changing our footprint, and that's the lithium-ion batteries. This was a first kind of, Sony released the first battery in 1991, but it was really the discovery in 1996 by Goodenough of the lithium iron phosphate electrode that really transitioned this technology into the modern day. Chang from MIT actually demonstrated a dramatic improvement. He founded his own company. That company got bought out. A lot of the stuff that, there was a big patent fight between Goodenough and Chang. Goodenough lost, even though there's some reasons to believe that he actually was the founder of the battery and most of the improvements were due to battery. So, and Chang won this battle. But you can see what happened in the meantime to lithium-ion battery. This is another example where entrepreneurs were able to have a fairly big impact on the field fairly quickly. But in this case, there was the guy that probably did most of the entrepreneurship, Goodenough at least, didn't actually profit at all from it, right? He basically made very little to no money off of it. So let's look at these numbers then. I want to kind of give you an idea of the clean energy from invention and application. So we've got these numbers. We've got the main payback. These are rough estimates, but when we really started to see these technologies take off, and money coming in, and what you'll find is that the time to market was over 50 years for silicon PV, over 20 years for the modern wind turbine, and something less than 20 years from LED lighting or lithium-ion battery. Now, the reason why this might be an issue is 20 years, a 20-year delay in taking something from invention to the marketplace is equivalent to about a 1 degree Celsius rise, 1 meter rise in sea level, and increased drought. So, and that has various consequences.
The leading southern flank of the Butte Fire blowing up as down canyon winds start to move a sea of sparks and flame here. We're just a little east of San Andreas, where this fire is continuing its march further into the foothills. The Butte Fire has now metastasized across 65,000 acres, nearly 100 square miles. At mid-evening, the flames again burning uphill, cutting off this road. One reason firefighters have to be so careful. These erratic winds have shifted 3 or 4 times in the last hour. Another reason the Butte Fire is still so dangerous.
So this was a fire that hit in September of 2015. I know it well. It did over $2 billion in damage with the Valley Fire put together. It destroyed 1,300 homes and 2,000 structures. So this is what it looked like from there. This is actually our house, which got taken down in the fire. It was so hot that even the wood burning stove was completely melted. But you can see that the fires are increasing. Part of this was due to, of course, poor forest management, but some of it is due, of course, to the increase of drought that is partially blamed on climate change. Now, this is a disaster, of course, of fairly big proportion, but it's also, I'm going to show it's also an opportunity. One of the things that's coming out now is that forest fires may produce as much CO2 as half of all fossil fuels burned. So it's really kind of an untapped and ununderstood way in which we can potentially look at and understand CO2 emissions and maybe reduce them. There's a lot of articles and research on this. But, for example, someone did a study in Indonesia which showed that the fires in Indonesia might have counted to 13 to 40% of equivalent to global human emissions. There's been studies that the increases in CO2 released might be accounted for by as much as 66% based on fires, and that there's some estimates in a science paper that suggest that fire produce emissions around 50% of the size of human emissions. So these are not numbers that we necessarily want to completely ignore. Of course, the issue here is that plants also, of course, uptake the CO2 at a very high rate once they burn down. So there's a balance here that is not well understood. And I'm not going to go into this graph. I'll skip that for now. Okay. But to make things even more confusing are reports like this. This is actually work done by Roger Bales at UC Merced. I wanted to mention he just basically got in the New York Times for the work he did on looking at the Sierra Nevada snow. And basically, the article has many points, but one of them is that, that the trees also affect the amount of water stored in the mountains simply by growing, and that they suck up water from the ground, which basically means these trees in the Sierra that have been growing at a much more faster rate than normal because we haven't allowed fires to progress, means that basically they're perpetuating droughts. That is, the trees growing are actually causing the drought conditions to get worse. Here's an example. Warmer temperatures also mean that trees grow faster and don't necessarily shut down for the winter. Thus, they use more of the melting snow in over a longer period. That leaves less. Whoops. Someone went off again. Okay. That leaves less water flow into streams and down reservoirs. So it might be counterintuitive, but the growth of trees in the Sierras might be reducing our CO2 emissions, but they're also perpetuating drought. Just shows you that the trade-offs are very much more complicated than we originally think, and that requires much careful studies, which gives us some entrepreneurial activities. So this also gives us a lot of benefit, right? We have millions of acres burned, thousands of homes destroyed, and billions of dollars to work with. That's always a good thing. So one of the things I've been working with, which is related to a citrus project I have, which is trying to understand, can we figure out ways in which to take these burned down lands and houses and stuff and use it as a method to basically build back in a sustainable manner. That involves not only in our land management but also in our homes. But to do that, we really need to understand, in terms of land management, how things uptake CO2, how we minimize water use, and how we reduce firewood use. And after studying this for probably a couple months, trying to see what I should do in terms of planting back 20 acres of land, I realized that we don't really have any data on the individual plant or species level to understand how different plants, native plants and species, really uptake CO2 and uptake water, and also transpire water. And the reason why we don't is because right now you have to use pieces of instruments like this, which are about $15,000 to $40,000, where you clamp this on the leaf of the plant, and you have to have a person out in the field to actually measure the transpiration rate from a leaf or the uptake of CO2 from a leaf. We have canopy measurements, but that tells you what the whole forest does. It doesn't tell you how to replant something that's been burned down to the ground in terms of the sapling level. We don't understand how freshly grown trees are going to uptake CO2. So one of my goals of the citrus project that I'm doing with UC Davis is to basically take one of these and design a very low-cost system that would be less than $1,000 that would also work completely remotely, so you would not have to have a person in the field. So we can analyze and understand automated, basically carbon uptake, water uptake, and leaf transpiration rates on individual plants, and that anybody could be able to use such a system for their own community to help them in basically guiding what plants they should plant for their land management, for best land management to maximize CO2 uptake and minimize water. So that's one of the things that fire opportunity has. And then the other thing, of course, that we're working on quite a bit is how to work with these communities, these fire-ravaged communities, to try to basically use new innovations that might come out to build net zero homes. So if you're going to build back a home and you've got, say, $500,000 insurance money, which is kind of roughly what we've got, you can now build back your homes being completely net zero and, in fact, even generate extra electricity. So they're better than net zero. And so we're working with these communities. And there's a huge funding and other opportunities there to basically build these fire-ravaged areas as demonstrations of net zero communities. So, so how do you then speed the transition? So I basically mentioned when we're talking about climate change and entrepreneurship, if you want if you want entrepreneurs to have an impact on climate change, you basically have to make sure they can do it very, very quickly. Which means you have to speed the transition from innovation to deployment. And there's two basic ways in which you can speed that transition as opposed to just using things, market conditions normally take their time, which takes about, say, 20 to 50 years. And that is you basically have to pick the right team, and you have to pick the right timing. I'm going to focus on this timing. I showed you how you can take advantage of natural disasters and huge influxes of cash from natural disasters to basically cause change to happen on a much faster time scale. But there's other things that can also help you. And I'm going to skip a lot of these because I want to go directly. I'm running out of time, so I want to go directly into what we're doing. One of the things I want to mention briefly that we've been working on is CAD-TEL. CAD-TEL takes advantage of both favorable policies and resource scarcity. And some of you know that CAD-TEL has made huge breakthroughs in the last few years. It's now at 21.5% efficiency. That means it's approaching silicon and is getting better than SIGs. So CAD-TEL was the poor child of the PV family. It's now no longer that way at all. And now some of the biggest solar farms in California going up right now are all based on CAD-TEL, not silicon. The issue here is this is what the tellurium price history is. And what you'll see is that the 2007 production was about 130 million tons, and a 1 gigawatt PV system would take about 90 of this. Okay, this is a resource issue. This is what I would call a resource scarcity problem. This becomes an opportunity for entrepreneurs to be able to basically come in, solve this problem, and have a big impact very, very quickly. And, well, how do you do that? Well, you have a couple ways of doing that. You can actually mine more, which is one way, or you can reduce the amount of CAD-TEL. These are a few micron thick, but there's no reason why cadmium telluride has to be a few microns thick. It absorbs all the solar intensity in about 500 nanometers or half a micron. So this is work we did in collaboration with Berkeley, actually. This is an invention out of Berkeley's lab. We can basically make CAD-TEL from nanoparticles, which gives us very, very smooth films that gets over some of the roughness issues with nucleation and growth type of mechanisms. And that allows us to make very good working devices that are only a few hundred nanometers thick. That gives us about an order of magnitude savings in materials. So instead of being able to build one power plant with 90 megatons, we could build 10. Okay. When we discovered this, which was back in 2005 or 2007, was when the invention came out. At that time, no one cared about CAD-TEL. No one cared about saving material because there wasn't enough CAD-TEL to bother saving. Okay? So this failed because the timing was wrong. Okay? This is why the timing is really important if we're going to do this. Nowadays, however, I'm not sure if I'm going to revisit this, but now this could potentially have a big impact. If we had just delayed the timing by 8 years, we could have potentially a big impact. The other thing I work on is this problem, which is there a way to produce more food with less resources with methods that are resilient against climate change? And this is another company we're working on to do that. It's called Soliculture. And Soliculture is basically a company that combines plant growth with photovoltaic power. We use a luminescent dye that basically allows us to capture the intensity of the sun and waveguides down to a PV panel where we convert the absorbed photons into power. But we also lose some of light that's not wave-guided. And that extra light happens to be picked in the color that plants really like. It ends up plants only absorb about 20% of the solar spectrum, even a little bit less than that. So, and they really like red light and blue light. So we basically just enhance that red light. And we've done this trials now for 3 or 4 years, and we always get either improved plant growth or neutral plant growth when we grow plants underneath our panels. So that means we can stick our panels directly into a greenhouse or a crop cover and generate power. So why is this interesting? Well, you can obviously just take a greenhouse and put ground-mounted PV panels right next to it. So why do we want to put them in the roof? And this is where timing is all important. I mean, there's some obvious things about we combine the module with the greenhouse structure. That's cheaper than having to build the greenhouse structure separate and then do the racking and labor and module separate. So we save money that way. Okay, but the bigger thing is this. Okay, and this has to do with favorable policies. Right now, you get a 30% tax incentive for installing PV, right? Well, if I put my PV in my greenhouse, because the greenhouse is the racking and mounting, it counts as that 30% tax incentive. Okay? So if I have a capital cost of 1 acre, let's say it costs me $180K to build a greenhouse. If I build it with 90% PV integrated, that increases the cost to about $780K, but then I can write out this entire $780K in my taxes. Okay, so that basically gives me, and there's other things, that gives me basically a greenhouse. I can buy the greenhouse with the PV integrated for less than I would cost the greenhouse without the PV. Okay, and you can carry that over. So this is just a timing issue, right? This is company, we're going to sell things, not because our technology is necessarily the best out there, but because we can take advantage of favorable policies into the system to basically get our stuff to market much, much quicker than we'd be able to alternative. Much faster we would be able to without those favorable policies. Okay, so I know I'm running out of time, so I'm going to wrap this up very quickly. So I'm going to argue that entrepreneurs will play a big role in climate change. And the reason for that is that climate change drives policies and urgency that allows us to transition from the idea stage to the commercial product stage much faster than we would normally do. Okay? For example, you know, I just showed you we have these tax incentives now that allows us to basically make a profitable company in 3 years, which maybe would have taken me 10 years without those incentives. We have the public that cares about things rapidly changing and are willing to invest in stuff that they might not have been able to otherwise. So the reason for this is that big impact, when you can see things like this happening from glass to drought, big impact drives very rapid timing. And that rapid timing is what's really critical to driving the markets and also the best teams to get involved, because the best teams want to be involved if they can get a very fast return on the investment of their time. Okay. And then finally, of course, the teams drive the innovation. So while history hasn't actually shown very much correlation between entrepreneurship being important for the technology we're currently using to reduce carbon emissions, it's only been in the last 5 years or so that we're really seeing the impact of climate change on our livelihood, and that's going to cause the right situation for us to drive for entrepreneurs to play a role in climate change mitigation. So finally, I want to mention on that note, I want to mention the UC-wide Carbon Slam. This is an event coming up in May 23rd at Xerox PARC, and involves the top 10 teams from all 10 UC campuses. The top team's going to give a pitch, kind of like the Grad Slam in PACS. We have a top team from each campus giving one in solutions. And we also have a poster competition. So the top 4 teams from each campus, there's some $20,000 in prizes that are being awarded. We've got people like Tom Steyer, who's our keynote speaker. He just announced yesterday that or a couple days ago, he's going to give $25 million to campuses to drive out the vote at swing states for students to get engaged in climate, to basically help students understand which candidates they should vote for if they care about climate change. But we also have people like Mary Nichols and John Picard and several VCs that run all the big clean energy funds. And then a whole bunch of CEOs. This guy just sold his company for $100 million. Dan Shugard just sold his company for $300 million. And I'm really happy to have a lot of great young women CEOs that have started companies who are also going to be there as part of the team. This is just a very partial list. If you go to our website, which is not on here, carbonslam.org, you'll get an idea of what the event is. But we'll have all our Carbon Slam champions from each campus announced by May 2nd, May 3rd. So if you're excited to see what the top people, what some of our students are doing from the 10 campuses in this area, tune out on our website and you'll be able to get a look at it. Anyways, thank you. That's all I have right now. And I'm happy to take questions. I didn't have time at all to go into my into CIED, but if anybody has any questions about CIED, I'd be happy to talk about that too. That's my Entrepreneurship Center.
Thank you, Sue.
Yes.
So we have time for maybe just 1 or 2 questions?
So I'm going to ask you 2 questions.
Sure.
Maybe you can tell me about CIED, and maybe you can tell me about Narendra Kapani.
Okay, sure.
I actually took the CIED. I was one of the first classes for
Oh, wow, that's good. Narinder Kapani is actually the person who started CIED back in 1970s, 1978, I think, or something like 1980s, maybe 1980, roughly. Maybe it's 1980. But anyway, he did this back in UC Santa Cruz. It was really kind of the first time that entrepreneurship was taught at one of the first places where entrepreneurship taught was a university. It led to a congressional testimony that led to really the embracing of entrepreneurial education on campuses. So CIED came back last year. I reinitiated. Kapani's actually endowed a chair in this position in this area, and we've got lots of activities. These are our activities. We run a pitch slam, a hackathon, a business showcase. We have a new entrepreneurship academy coming this summer. I want to show you, if people like Steve Blank giving our kickoff for our hackathons. Our hackathon is going to be on Beyond Geek TV. They came in and filmed our entire hackathon. PBS did, and we're going to have a television show based on our hackathon on PBS. So you can see we had all these mics and stuff. 550 people. I had to feed all of them for 3 days. It was an interesting experience. And we did this by literally pulling up our little minivans into Costco and ordering 200 pizzas and 500 muffins. But these are just kind of ideas of some of the things that came out of CIED. This was a virtual reality office. We had a labor tech person that we had on our Walmart Connect, but we had someone who actually did an Amazon app that when you buy things on Amazon, it puts a little thing of code next to what you're buying based on the labor practices, so you could actually see whether or not what company you're buying your stuff from, whether they had good or bad labor practices. We had something that rated your skateboard performance, a little Arduino kit that sat on the front. But anyways, there was a whole huge numbers of them that some of them went on to our business design competition, which we just finished up this is an old thing, but we just did that a couple weeks ago. So anyway, I just wanted, this is also, the UC delegation is now in Hanover Messe this week. UC system only brought 2 teams across the entire UC system, and one of them is our team from UC Santa Cruz, so we're very proud about that too. So anyway, yes, you were with Narinder Kapani, did you really?
This is first class. I was probably, you don't remember me.
You'll have to tell me your name, because
I was also responsible partly for the dance slide.
Oh, really?
So this is kind of the chaos stuff.
Well, I have lunch with Narinder next week, so I would love.
Yeah, I'll give you my
Yeah, that would be great. He's 92 now or something like that. But he's a great guy, and he is so sharp.
Thanks, everyone, for coming.
Yeah,
I'm just going to let you all carry on.
Yeah,
we need to conclude.
Thank you.
Thank you. Thanks, Sue.